Last lesson we talked about different types of force, and this lesson we're doing about something called resultant forces. So lots of forces act on an object. So it's not just one force. And these forces might act in lots of different directions. So you might have forces down and up and left and right and forwards and backwards and all of that. So we can consider the size and direction of the forces. And so let's remember, if it has size and direction, then that means it's a vector quantity. So we did about that in the first lesson of this topic. So remembering that force is a vector, which means that direction matters. Okay, and we can replace all of these forces, all of these different forces, with one single force, and that single force is called the resultant force. Okay, so we can consider the size and direction of these forces to replace it with one single resultant force. Okay, so resultant force is the kind of key term for this, and it just means the kind of overall force that takes into account the size and direction of all the other forces that act on it. So what does this look like? Well, we're going to split this up into balanced forces and unbalanced forces so that we can kind of have a look at it. And kind of true tradition, we're going to think about a box and somebody pushing a box. So now I have to draw. We know that my art skills are terrible. Okay, they look like they've got a broken leg, but never mind. So we've got somebody pushing a box, and we're going to say that they are pushing forwards with a force, and there is a force acting in the opposite direction, which in this case would be friction. Okay, so if these forces are balanced, then balanced forces, then there is going to be no resultant force. So let's remember from probably year 7 when we did forces that the size of the arrow represents the size of the force. We can see that these arrows are the same size and they're in opposite directions, so they will cancel each other out completely, which means that they're balanced, and it means that there is no resultant force overall. Okay, so we need to know what happens when there's no resultant force, when the resultant force is 0, and this is basically Newton's first law of motion. So we talked last lesson about one of Newton's other laws, but this lesson we're talking about Newton's first law of motion, which is basically that if something is stationary at rest, it's going to stay at rest if there is no resultant force. So if it's stationary, it stays at rest, and if it is moving, it moves at a constant speed. Okay, so if there's no resultant force because the forces are balanced, then either it's going to be stationary or it's going to be at a constant speed, and which one of those depends on whether it was stationary to start off with or whether it was already moving. Okay, so this person who's pushing this box, if the box is stationary and they're trying to get it moving in the first place, the box is still going to be stationary. But if they're already moving the box, then this box is going to be travelling at a constant speed. So it does depend on the context. And in an exam question, they would tell you about the context. So you need to read really carefully to make sure that you've understood whether or not they're talking about something that is going to be stationary or whether it's going to be moving at a constant speed. So now if we think about unbalanced forces, so let's have our box and our person pushing. Okay, so now they're going to push and they're going to be pushing more. So the forward force is going to be bigger, but the friction is going to be the same. So for this, because the size of the arrow represents the size of the force, okay, we can see that, and they're in opposite directions, therefore it's going to be the difference between these two sizes that is the resultant force. So if we kind of look at this orange arrow, if we moved it, if we looked at what proportion of the pink arrow it kind of takes up, so going up, that means that that part of the force would be cancelled out by the orange bit. Okay, so the resultant force would be this bit that's left over. Okay, so if they're in the opposite directions, then it is the difference between the two arrow sizes. If they're in the same direction, then we just add the values together. Okay, and we can think about what happens with the motion for this box as well. So in this case, this box would be speeding up because they're pushing it in this direction and there's a resultant force in the direction they're pushing it. So therefore this box would be speeding up. So that's this example, okay? But it could be slowing down if it was a situation where, if we've got a pink arrow, if our orange arrow was bigger, then it could be slowing down if there was an unbalanced force on it. Okay, so I think the next topic that we talk about motion. So we talk about objects moving, speeding up, slowing down, travelling at a constant speed, and we'll look at motion graphs. But all of it does link together, and you could be asked questions in your exam that link together the forces that are on an object and the motion. So always think about whether it's going to be balanced or whether it's unbalanced. If it's balanced, it's either going to be stationary or travelling at a constant speed. If it's unbalanced, then it's going to be speeding up or it's going to be slowing down, depending on which direction the resultant force is in. I'm going to answer some questions. So as we've done before, I read the question out and highlight it, pause the video, try and have a go at answering the question, then go through the answer. Questions 1 to 6 I'd like everybody to try, and then 7 and 8 are the extension task, please. So a cyclist on a bike has a thrust force forwards of 1,600 newtons and the wind blows towards him with a 500 newton force. What is the size and direction of the resultant force? So they're in opposite directions. We're going to find the difference between them. So 1,600 minus 500 is equal to 1,100 newtons. And we need to do the direction as well, with the bigger forces going to the right. Or we could say forwards. That's fine, any of those terms. In the grid below, each square represents 1 newton of force. State the size and direction of each force arrow. If we look at A to start off with, so we need to go from the end of the arrow to the very tip of the point of the arrow. So 1, 2, 3, 4 squares, which would be 4 newtons, and we can just say right. For B, 1, 2, 3, 4, 5 newtons left. And for C, we can just use a bit of maths. Okay, so we could imagine this to be like a triangle, which we've done about in maths, and it is a right angled triangle. So we can use Pythagoras for this. So we've got 1, 2, 3, 4 squares. So remember that Pythagoras is that the square of the hypotenuse is equal to the sum of the square of the other two sides. So we're going to do 1, 2, 3, 4 squared plus 1, 2, 3, 4 squared. So 4 squared plus 4 squared is 32. But that's the square, that's what c squared is. So c squared. So therefore we need to do the square root of 32. Oops, square root of 32, not 3, is 5.65685, etc., etc. So if we just round it to two significant figures, then that should be fine. So 5.7. And then we need to say about the direction. So we're just going diagonally up and right. Or we could say northeast. If we think north, east, south, west, that would be fine as well. We could also give a bearing, which going an angle from north, and that would be 45 degrees. So we could say that has a bearing 45 degrees. Any of those things are acceptable. When we talk a bit later on about kind of we're going to do a bit more about kind of vector forces, and we will talk about angles a little bit more then. So it's always worth kind of thinking, can you do something with Pythagoras? Can you do something with kind of angles? Two forces of 15 newtons and 36 newtons are acting on a body. Calculate the possible resultant forces and directions when the forces are acting in the same direction from left to right, in opposite directions, and then at right angles to the body and to each other. Draw a diagram to help. Okay, so if they're going in the same direction, then we're going to add them together. So 15 plus 36, 51. And if it's going from left to right, then that's going to be going right. If it's going in opposite directions, we find the difference. So 36 minus 15 is 21. And that's in the direction of the 36 Newton force, because that's the one that is the bigger force. Because it doesn't actually tell us which direction it's going in. Okay, if they're going at right angles to the body and to each other, draw a diagram to help. I went a bit wrong, so I've stuck over a piece of paper, which is why you should use pencil. Okay, so we've got two forces, a 36 Newton force and the 15 Newton force at right angles to the body and each other. Draw a diagram to help. So if I've got, say, 15 newtons down and 36 newtons across, then the resultant force is going to be somewhere in between these. Okay, so I want to draw a triangle really. What I can do is, so the resultant force is going to be somewhere here, and this is going to be 15 newtons still, because I'm just shifting it across. Okay, so I can use Pythagoras again. So I know that the resultant squared is going to be 36 squared plus 15 squared. It's going to give me the resultant squared, so let's do this. 36 squared plus 15 squared is 1521, but I don't want that. Is the square root of 1521, which is 39 newtons. Okay, but I need to know the direction as well. Well, it is a right angled triangle, so that means that we can use trigonometry. So if we want to have a think about which one we want to use, although we do now have the hypotenuse, we calculated the hypotenuse, so it's usually a good idea to kind of, where possible, use the values that you've been given, because you know that they're definitely right because they gave you them, whereas if you use the one that you've calculated, there is the possibility that you didn't get it right. So if this is the angle, so we're going to do the angle from the horizontal, that's fine, the angle from the 36 Newton force. So I have the opposite, which is the 15 Newton one, and I have the adjacent, which is the 36 Newton one. So we're going to use TOA. So I know that the tan theta, theta being the angle, is going to be equal to the opposite over the adjacent. The opposite is 15, and the adjacent is 36. 15 divided by 36 equals, and then tan to the minus 1. Sorry, I don't know why I pressed divide. So therefore, theta is going to be 22.61986, blah, blah, blah. So let's just do it to 3 significant figures, 22.6 degrees, and that's from the 36 Newton force. Question 4, what is the resultant force in the box? In which direction will it move? So we're going to, there's 2 ways that we can do this one. Either we can find out the forces to the left and the forces to the right and then work out the difference between them. So let's do that first. So 14 plus 5 is 19. 7 plus 5 is 12. And then we'd find the difference. 19 minus 12 is 7 newtons. The other way that we can do it is think there's a 5 Newton force here to the left and 5 Newton force here to the right. So they cancel each other out. So we only find the difference between 14 and 7, which is 7. And it's going to be in the direction of the 19 Newton, so let's say left. What are the resultant forces on the box, and which direction will it move? So now we've got them in not just 2 like directions, but in 4 different directions. Okay, so let's work out a resultant for each direction and then an overall resultant. So 12 plus 3, we've got 15 newtons. 6 plus 3, we've got 9 newtons. So 15 newtons left, 9 newtons up, 6 newtons right, 18 newtons down. Okay, so let's think horizontally to start off with. Horizontal, we've got 15 and 5, 6. So 15 minus 6 is 9 newtons. To the left, and then vertical, we've got 18 minus 9, which is 9 newtons down. Okay, so that's not quite enough for the higher paper because you've got 9 newtons down and you've got 9 newtons left, so your resultant is going to be this here. Hopefully we can see that this is a 45-degree angle. So you give a bearing of 225 degrees as the direction, or you can give it as 45 degrees from like the downwards force. It doesn't, they're quite lenient in exams about how you give your angle. But don't just say like down and to the left, because you're not going to get a mark for that on the higher paper. So we can use Pythagoras again. So 9 squared plus 9 squared, and then we want to do the square root of that. So 9 squared plus 9 squared is 162. And then we want to do the square root of 162, which gives 12.7279, blah, blah, blah. Let's do it to 3 significant figures, 12.7. So 12.7 newtons at a bearing of 225 degrees. Okay, look at the diagram below. The biker has put the bike in gear and is turning the throttle slowly to apply a slight driving force, but he's also applying the front brake. The bike is not yet moving. The questions are about the effects of forces in equilibrium. Label the 2 forces acting on the motorbike. The 2 forces are in equilibrium. Explain what this means. Okay, so this arrow going forwards we would call the driving force. That's given in the question. up here, says it's a driving force. And the other force, the backwards force, he's applying the brake, so we could call it a braking force, that's fine. It's actually friction between the brakes and the wheel, but braking force is okay in this situation. Two forces are in equilibrium. We'll explain what this means, that they are equal and opposite. So equal in size, opposite in direction, cancel each other out. Describe what will happen to the motorbike if these forces remain in equilibrium. Then it's going to remain stationary because it's got a 0 resultant force. And it's not yet moving, so therefore it's stationary at the moment. It's going to stay stationary until there's a resultant force on it. These questions are about the effects of resultant forces. The biker now releases the front brake. Describe how the motion of the bike changes. So if they release the front brake, there's not the braking force, so there's just this driving force that's going forwards, which means that it is going to accelerate. So it will accelerate, so it will speed up. Oh, I wrote it in the wrong thing, silly. Different backwards forces now act on the bike. Name one of these forces. There's still going to be drag or air resistance. And there is going to be some friction between the tyre and the road. Eventually the backwards force becomes equal to the forwards force. How does the motorbike move now? Well, it's accelerated up to a speed and then the forces become equal. If it's at that speed, then it's going to remain at a constant speed. The biker approaches a red light. Explain how the forces on the motorbike will change as the biker releases the throttle and applies the brakes, and what effect the forces will have on the motion of the bike. Okay, so if he releases the throttle, there is no longer a driving force because they've released the throttle. At the same time as this, they've applied the brakes, so they've increased the braking force at the same time. So there is a resultant backwards force, which means that it will slow down until it stops. Okay. Look carefully at the forces applied on the plane below. Answer the following questions. Label all the forces acting on the plane on the diagram. So downwards force is going to be weight. Up, the opposite of weight is lift. And then forwards force we would call thrust. Backwards force we would call drag. Okay, the plane is flying along a horizontal line. Describe the motion of the plane in this situation. So we can see that the lift and the weight are equal, so it's not going to be moving up or down. But we've got 58,000 newtons thrust, 12,400 newtons drag. So the thrust is bigger, so it's going to be speeding up or accelerating. Okay. How would the vertical forces change if the plane were to start flying diagonally down in a straight line? So if it was to start, so it's travelling like this at the moment, if it would start to travel diagonally down, then the lift would have to decrease. Okay, so let's think about this logically. The weight is the mass times the gravitational field strength. You can't change the mass of a plane once it's in the air. We certainly can't increase it. We could technically decrease it by chucking stuff out of it, but we can't increase the weight to increase this force. Okay, so if we want it to start moving down, then we've got to decrease the lift. Okay, so the lift would have to decrease because the weight cannot So that's a question where you have to think about the context that it's being given in. Your gut feeling would be, oh, we'll increase the weight of it, but if you've got a plane in the air, you can't start adding weight to it. Calculate the horizontal resultant force on the plane. So we had 58,000 newtons forwards and 12,400 newtons backwards. So we find the difference between those. Whoops, 58,000 minus 12,400, 45,600 forwards. The runner in the picture is running with the wind pushing her forwards. The backwards friction force on the athlete is 42 newtons. The forwards force of the wind is 21 newtons and the force from her muscles is 84 newtons. Complete the diagram by adding force arrows to show the forces acting on the runner. Make sure the arrows are about the right length. So if we want to make sure they're at the right length, we need to use a ruler and a pen. We've got a backwards force of 42 newtons. So if we do 42 newtons, let's do 4.2 centimetres. So I'm going to draw that from where her foot is because, whoops, I did it too long, never mind. Okay, so 4.2 newtons is friction. And then forwards force of the wind is 21 newtons, so 2.1 centimetres. Wind, and then her muscles is 84 newtons. So 8.4 centimetres muscles. Calculate the resultant force on the runner, give its direction. So I've got, it's obviously going to be forwards because we've got bigger forces on this side. So we're going to have the wind plus the muscles, so 21 plus 84 minus 42, which is the backwards force of friction. Okay, so 21 plus 84 minus 42, 63 newtons. Could have done it in two separate calculations, working out the forwards, but as long as we're using, well, yeah, it's good practice to use brackets. Describe and explain the result of these forces on the motion of the runner. Okay, so let's start with the basics. The runner is going to accelerate. The runner will accelerate forwards, and the reason the runner will accelerate forwards is because there is a resultant force, forwards force. Okay. However, as you accelerate, the drag increases. And you will have experienced this, like if you've ridden a bike, the faster you go, the more you can feel the air resistance in your face, because you're going through like more particles per second that are going to cause that resistive force. So the drag increases, and so her acceleration decreases until she runs at a constant speed. When the runner has passed the finish line, she decelerates by decreasing her muscle force. Calculate how small her muscle force must be before she decelerates. Show your calculations. Assume that the friction and the force of the wind have not changed. Okay, so in order for her to decelerate, then we need to have a slightly bigger friction than wind and muscles. Okay, so if so we had the wind was 21 and the friction is 42. muscles to equal the friction minus the wind. So 42 minus 21, which is 21 newtons. So the resultant force is a single force that has the same effect as all the forces acting on an object. If this is 0, the object is stationary or travelling at a constant speed. If this is greater than 0, the speed or direction of an object will change.